Hey, Physics 30s, how's it going? So we are going to start our new chapter. This one is on the object nature or the particle nature of EMR. So the last unit, or last chapter, I should say, the larger one that we did, was just talking about how light behaves as a wave and all the different characteristics that are attributed to waves, such as reflection, refraction, diffraction, polarization, interference. Other ones would be like they travel all the same speed, they have a wavelength, they have a frequency, and we have a bunch of different characteristics that all behave as if the waves. But there are experiments that have been done in the past by Einstein, by this guy named Maxwell Planck, Gilbert Lewis, a few other scientists that you're going to see, De Broglie, I can't think of any ones right now, Bohr. There's going to be a few scientists that can't explain, the scientists can't explain their experiments using the wave model. So they had to think of them light as something different, something that was behaving not as a wave, but behaving as a particle. So there's a lot of controversy at this time of this nature where scientists are like light as a wave, and then there's a school of thought saying scientists were saying light as a particle. And then eventually it all comes together and say light behaves as a wave or particle depending on which experiment you're doing. So we are going to talk about this object nature, or the EMR nature of light, or the object nature of EMR, I should say. Okay, so this first part, like, where does this idea come from? Where does the birth of the quantum mechanics or the quantized thought of light come from? Well, it comes from the idea of this, that they couldn't predict the color produced by an incandescent object. What I mean by that is like you take a red hot or a white hot glowing object, and you were to pass that light through a prism and it would separate into a rainbow. They couldn't predict mathematically, right? Obviously they could see what this the wave and the amount of energies of each of the photons each of the wavelengths that are coming out. They could see this curve, what they call the Blackbody curve, pretty easily. They have a lot of good measurement devices for that. But the classical physics couldn't explain this. Right? So according to classical physics, that if you heat up an object, it should just keep on releasing shorter and shorter wavelengths until something happens. Until, according to this, it concludes that, like, if you were to strike a match, all the light in long wavelengths and more in the shorter wavelengths, well into the X-ray and gamma rays, and it would continue into the universe is just incinerated. That's what, according to classical physics, that's what should happen. Obviously, it doesn't happen, right? They call this the ultraviolet catastrophe just because it's a catastrophe in their math, not because it actually happens, right? Obviously, the world didn't incinerate itself. So we had to develop a new school of thought. So we brought up this idea of what we call a black body radiator. And then rather than me trying to explain what a black body radiator, because it's a difficult subject sometimes to talk about, like, how does it actually work? What is a black body radiator? How does quantum mechanics play into this? How does this idea of photons, packets of energy, explain this black body radiator shape, this kind of curve that you see here where it goes up, then down, then it kind of peters off a little bit. How does this work? Well, I want you guys to, if you haven't done it already, stop this video or pause this video where it is, right? Come back after you watched the links that, I don't know if one of these two links work, but the links I've shared in the Google Classroom, watch both of those, and I'll be here when you get back. Okay, so hopefully those videos help you, or help explain what this ultraviolet catastrophe was, this Rayleigh-Jean law that was obviously wrong, and they knew it was wrong. So along comes this guy named Max Planck, right? So this little happy little guy on the side I have over here, right? So he came along and doing his other experiment regarding transfer of heat between objects, he discovered that light behaves as a particle. It comes in these little packets of energy, and he has this formula here, E is equal to NHF, where H as the physics girl mentioned, is the Planck's constant. You can find that on your formula sheet. So let me just pull my formula sheet out here and show you. So right here, the bottom of my formula sheet, on the constant side, I know it's kind of blurry, sorry. You'll see it's just right above the atomic mass unit. It says Planck's constant, and there's two values over here. There's two values. One of the values is the value that you saw in the video, the 6.63 times 10 to the negative 34 joule seconds. But there's a number below it that's in electron volts there. It says 4.14. Is it going to focus on me for me? I don't know. There it is, 4.14 times 10 to the negative 15 electron volt seconds. So remember that in the previous chapter, like 2 chapters ago or so, we talked about this unit of electron volts to measure energy of very small amounts, like 10 to the negative 20 and 10 to the negative 19 joules. So we're going to be using that again because we're going to be talking about small amounts of energy. So this H could either be one of those two values. It doesn't matter which one you use. It does matter depending on which kind of question, what you want to do with that number after the fact. So if you wanted to communicate, you usually use electron volts. If you want to do more math afterwards, use joules, like maybe trying to find the speed of an electron or something. So we have this nice little formula he created. This E is equal to HF. I'm sorry, I'm kind of looking the wrong way here. I'm looking over here. This is where my screen is, but even though it looks like it's over here. I know it's kind of strange. My image is not flipped anymore. I'm using a different program. So this N here, usually that N doesn't show up. You notice on the formula sheet, I don't have a newer formula sheet. I believe you guys do have a newer formula sheet, so all the formulas that we're going to be using up in the top corner. But my formula sheet, they just put it down on the bottom here. In your formula sheet, this kind of all gets pushed down. The whole middle column gets pushed down a little bit, and this gets put up onto the side over here. Right? But we're going to be using the formulas on the top there, and one of them says E is equal to HF, E is equal to HC over lambda. But you notice there's no N in that formula. The N is just the number of packets. You'll see that we'll use this later on, like when we're talking about how many photons a light bulb is releasing per second. It's releasing a lot of photons, right? A lot of different little packets. We've got to figure out how many packets there are that kind of add up to this larger number that a white light bulb would be releasing, because 100 joules is trillions upon trillions upon trillions of photons. So that N is going to be a pretty big number usually. Most of the time when we're calculating this, we talk about just one photon. When we talk about just one photon, we just say that N is usually equal to 1, unless we're trying to find it. And you're going to see later on when we try to find that N, maybe I'll put that N back in. So we have H is his constant, right? It's either 1 or 2 values. Oops, sorry, I'm going to write this down in a different color, hopefully. All right, so it's this one, or it's the 4.14 times 10 to the negative 15 electron volts seconds. Now, you could just convert between these two, because you could use that 1.6 times 10 to the negative 19 number that's on the formula sheet too, just slightly above it. Right about there, about halfway down the sheet. All right, so that tells you the conversion between electron volts and joules. Now, F is the frequency of light. Now, remember what I said before, if I don't say the word visible light, when I say light, I usually mean EMR. So this actually probably better be stated as the frequency of the EMR, because all EMR behaves as if these little packets of energy. Okay. This idea, classical physicists couldn't quite internalize this idea very well back in the day. That think about like in the idea of like a pendulum that swings a nice continuous smooth motion around, rather than being nice and continuous smooth amounts of energy, it would have this much energy, and then it would kind of jump to another amount of energy, and then jump to another amount of energy, jump to another amount of energy. And then it wouldn't have any energy in between the swings. It would just be like a little staircase around, where it just jumps from one form of energy to another form of energy, or a quantity of energy, one quantity to another quantity to another quantity to another quantity, and there wouldn't be energy in between. It didn't make sense to them. They didn't like this idea. So that's okay. right? A lot of quantum mechanics, a lot of physicists still don't understand or don't quite get it. I honestly, I don't get it, right? It's a hard topic. Okay, so Einstein and this guy named Gilbert Lewis expanded on this hypothesis of just being packets of energy. He just said that the energy is not just being released by the matter itself. So remember, like in the curve, they were just talking about the Blackbody curve. They're talking about heating up an object, it's releasing energy in packets, right? He wanted to expand it and just said light. All of light is in these little packets of energy. And this guy, Gilbert Lewis, if you do some chemistry, you'll know Gilbert Lewis as well. He's a famous chemist. So here's Einstein and Gilbert Lewis down here. So they coined this term photon for these little packets of light.